we proved f of a being 1 over 2 pi I, c containing the singularity f of z divided by c minus a dz, right? That was fairly easy. And f prime of a was 1 factorial, which is just 1, 2 pi I c, and I just showed you the important part of the proof, fz dz. We have these two things, right? Good. And next thing we're going to do is the fact that f prime of z is continuous, but we did that last time, right? Using this version in here, right? That's what we did last time. Remember, we used this Cauchy's integral formula, and we proved last time that f prime of z is continuous. All right? So we looked at f prime of b minus f prime of a as b approaches a. Remember that part? And we show that this one is approaching 0. What did we use? We used that. Now today, in the homework, we prove this one is also true. So f prime of z is now continuous. Now here we're going to prove that. It's a new theorem today. F prime of z is analytic. Remember those first two examples in the homework? In the real function, f is differentiable in the entire real line. That doesn't mean f prime of it is differentiable, right? It could be all defined, but it's not differentiable anymore. So differentiability stops for some example in real value quickly. But here it seems like once it's differentiable forever. And I said that last time, and it's interesting phenomenon. So here's the proof. Since f prime is continuous, integral of all sorts of things is defined, f prime of z, of whatever path we consider it exists. Do you know what theorem this one is? Some function here, I didn't differentiate anything. There's some function is saying continuous, then integral exists. It was Riemann integrability theorem. That was some boxed item in usual Calculus 1 textbook, but nobody proves that in the Calculus 1 level. But that's the important theorem. So this makes sense. Then we can do whatever is necessary. So this exists, therefore we applied Moreira's theorem. Before we do the Moreira's theorem, let me do this. Now, compute this thing that we're looking at, f prime of z dz. Well, this whole thing is analytic whatever where we are, and it has antiderivative, right? What is the antiderivative? So let's say c looks something like this. It doesn't have to be simple. You know, it starts in here and ends there, things like that. We started with f and it differentiated f prime. So antiderivative of f prime is f, right? And f is analytic. It's defined everywhere. Think about that problem we just looked at it here. This one was a problem, and its antiderivative is not defined everywhere outside A. It has a branch cut. But this one doesn't have a branch cut. Why does it not have a branch cut? Nope. Its antiderivative is fz, and fz is analytic, right? Fz is it. That's how we started. So fz exists. So starting where? C0 ending at where? C0. So it's just supposed to be 0. So no matter what loop you put in that region R, it's going to be 0 all the time. Remember this theorem? If some function whose integral is continuous, we know it's continuous, so that was actually the hypothesis of that theorem. If you integrate closed loop, it turns out it's always 0. Then what conclusion do we have? And what is a theorem? Starts with M. Realize that this type of thing really helps. Theorem says f prime of z is what? Morera's theorem? Morera's theorem. If the integral is always 0 and the function you're integrating is actually what? Nope. That's Liouville's theorem. Analytic. I introduced this one alongside with, what is it? Fundamental theorem of part 1 that asserts the antiderivative exists. Okay? So the two big theorems used, Morera's theorem and this particular version of Cauchy's integral formula that allows us to conclude f prime of z is actually continuous. So then Morera's theorem says, all right, f is analytic, then f prime of z is also analytic. Okay? It doesn't stop. Here's a corollary to this theorem. F is analytic, f prime is analytic, right? F prime is analytic, then what is analytic? F double prime is analytic. If this is analytic, F triple prime is analytic, right? And it goes forever. If all derivative exists and they're analytics. Right? So here, i.e., all derivative are analytic. It's not just about point A. All the neighborhood has a derivative analytic. And this is important part so that we can consider Taylor series, a power series. Real valued function, it has actually a very nice thing that was introduced at the end of the Calc 2, but it's a very limited example. E to the x, sine x, and cosine x. There are not much other things they consider because it's a limitation. They don't have this one. They don't have any differential function in here guarantee that these guys all exist. There's another hurdle, which is known as a Cauchy's inequality, that you saw that Cauchy's inequality allows this Taylor expansion actually exist for all analytic functions. There's no exception. That's an amazing thing that is happening in the real complex variable. So that's important theorem. So let me do this guy in the street joke. If a guy in the street grabs you and asks you, why is all the derivative analytic function is analytic? And then what is the two things that is involved in there? Cauchy's integral formula and Morera's theorem allows us to conclude that everything is all analytic. Okay? I usually prepare the better explanation so that it's not just this theorem and that theorem implies it. That doesn't really insightful. But I failed. This is pretty difficult to explain intuitively why this happens. But this is the formal proof.